Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour.
Hello and welcome to our first episode of On Air Actually Rocket Science. I'm Mikkel and I'm joined by
Flo.
We are doing this podcast and interviewing several professors from the Department of LRG. Today, Professor Fenna Sahoud joined us and we are very glad that you're here. And could you maybe please describe yourself a little bit?
Yeah, many thanks. I feel really honored to be the first and to support this format. Should I introduce myself a little bit? Yeah. I'm Fanas Daoud. I'm 49 years old. I grew up in Syria and studied civil engineering in Karlsruhe. I made my PhD in Munich. Afterwards, I joined Airbus for roughly 17 years, and I'm rather fresh professor here. Started September this year at TUM, and here I am.
How about we start with a quick game, this or that?
Yeah, so basically the idea of this concept is that we will ask you a question and you just give us a quick answer, which one you prefer or what you like best. So first question would be, first on board or last call?
First.
First on board. Okay. Well, you just took it a bit away when you introduced yourself. Question would be Airbus or Boeing?
What a question. Yes, Airbus for sure.
Okay. Spacecraft or aircraft?
Aircraft.
Okay. Industry or academia?
Academia.
So the first is we would like to know about the civil engineering you you studied in Damascus, like you already said, in Syria. How did it come? You were studying there.
Yeah, actually, I'm Syrian German. So I have a Syrian father and a German mother. Grew up in Syria and came to Germany in the age of 22. So naturally, let it put other words. My father is a civil engineer. So to be honest, I never thought that I will follow him, but it happened. So I started civil engineering in Syria, and when I came to Germany, to be honest, I did not dare to change my education, though I would have loved to. But it appeared to me too dangerous to migrate to a new country and to change my study. So I sticked to civil engineering.
Okay.
So you moved to Karlsruhe afterwards for studying your diploma. What was the difference between Syria and Germany in general?
It's rather a big difference. So Syria is a development country, you would say. So the education is good, but it is too much theoretical on the one hand and low level. So I struggled a bit to catch up with the German level on the one hand. On the other hand, since I already had my degree, I could concentrate on learning the language on the one hand, and on the other hand, to select the topics that I really like, mainly structure engineering. So keep it short. The education in Syria hasn't been that time not bad. Today, unfortunately, and I think everybody knows that Syria is almost destroyed. So there's almost no education there. But that time, the education has been profound enough so that it provided me a good starting level for Germany. Nevertheless, the level of the education in Germany is much higher.
Okay. After that, you finished your diploma. You moved then to Munich to do your PhD at the Technical University here. How was another move? Yeah.
To be honest, I've been used to moving. So moving from Syria to Karlsruhe has been, there has been an intermediate step. So I went to, I recall the name of a small village where I studied German in Goethe Institute, but afterwards to Karlsruhe. And moving to Munich hasn't been that difficult, except for the prices. So Munich has been compared to Karlsruhe, incredibly expensive. So the flats has been very, very, very expensive. But it's been, so I never regretted coming to Munich, just because, if I tell you that in other words, in Karlsruhe, I had the chance to concentrate on what I loved, mainly programming, rather complicated methods in structure engineering. And there I won a prize of the best scientific work for 2000 for the city Karlsruhe. And based on that, I got the offer from Munich to come to Munich to make my PhD. So I followed that without knowing what's going to happen, let's say. So when you start a PhD in a new city, it's you start from scratch. But I never, I've been confident that this is the right step. And to be honest, and for the guys who are listening and watching us, so there are many disciplines in the world where it's probably not worth making a PhD in engineering, and especially in aerospace engineering. It's pays off. So the difference between the current state of the knowledge and what we can teach in bachelor's and master's is still big. So there is a lot of room to learn. So I enjoyed really my PhD in Munich.
Okay. Afterwards, you left academia and went to Airbus. Could you maybe tell us what your first project was there?
Let me remember. So it's been the A380. We worked on the root rib. So it's part of where the wing intersects with the fuselage. And you can imagine this rib in small aircraft is as big as an arm. In an A380, you could have two people on top of each other in that rib. So it's a huge, massive component. And we performed the topology optimization of that rib. So we had to save a lot of weight. And so it's been my first work for the A380, a civil project. Though I joined in Ottobrunn that time, so it hasn't been Manching, it's been Ottobrunn, more or less, 100 meters behind us. I started there and in the military air systems. But we had a lot of civil engineering projects, and the A380 has been the first one.
Okay. The question just off the road. If you would finish today with university, would you start again working at a major company, or would you found or join a startup?
I would definitely join a big company as my initial step in order to learn how things are working, especially in the aerospace engineering. So in our education, in my opinion, it's rather difficult to start with a startup. Moving afterwards to a startup might make sense. There are many reasons for that, but learning how things are working in practical application makes sense in big companies. Yeah. So I would repeat that anytime.
Okay. You also worked on the space plane. Could you maybe explain the general idea behind it?
Oh, you are touching a rather emotional part. So the space plane has been a kind of competing project to the other space planes developed around the world. And the idea is to find an aerospace vehicle that approaches the space, the vicinity of space. So space is defined to be, just a formal definition, at an altitude of 100 kilometers. And many people around the world were competing to find a vehicle, to develop a vehicle that flies somewhere from an airport, approaches the 100 kilometers, and lands again in a civil airport. And the idea is, on the one hand, space tourism, but also a lot of explorations. We wanted, for example, also to launch microsatellites. So you must not develop a rocket that flies only once. If you have a reusable vehicle that is capable of launching microsatellites, and there are plenty other applications. But so microsatellites and space tourism were the main focus for the space plane.
Are there any difference to other space tourism companies?
So if you work at Airbus, safety is the most fundamental thought you have. And I would expect that this is also the reason why the current space plane is in the drawer. So there, to my knowledge, there will be no European space plane in the next years to come. Just because it seems to be a rather complicated endeavor. And so thinking about the American colleagues, they are much more willing to take risk in both in capital, so investing money on the one hand, taking the risk, and making a product that is risky in general. And this is something you could see both. This is part of our European DNA. Could be a drawback in the competition and could be also a benefit. So I think anybody could make his thoughts what he prefers.
Could you maybe tell us why it was an emotional project for you?
It's been the first project that I led from structure point of view. And it's been a rather small team. So we were, I don't know, at most 50 people from smaller departments, so driven by space. So the space colleagues were leading the whole project. But from aircraft point of view, since it's a hybrid product, so it's something that's flying, and then where a rocket will be ignited and you will fly to space. So there's been aircraft engineers, and I've been leading them. So I've been involved in every bit and piece in that project. I spent overnights thinking how to improve, how to do things. And I believed that our design might be really superior to the American one. And I thought that we will be that courageous to bring that to space. So it's been my first big project on the one hand. On the other hand, I believe that it will be a unique vehicle that I might be involved in. So yeah, it's really a pity for me personally that this project is now at least on ice.
In the end, this project didn't finish. Could you explain us why it failed, if you can say that?
So I wouldn't say it failed. It's a kind of, if you work in aerospace engineering, you will be surprised that most of the work you are involved in will never fly. Just because you have so many concepts, so many ideas, so many business that might appear, you work on, and only few of them get realized. So this is nothing unusual on the one hand. On the other hand, I think the main reason we wanted to have partners for operating that. So we would not like to operate it from Europe, and we wanted to have partners from overseas or from Asia. and those partners didn't show up. So we had a lot of negotiations, but none of them were that successful that we could continue the project. So finally, it is the funding to find enough capital. And this is what I mentioned with, I would say personally, this is one of our drawbacks in Europe, that we have too few, too little risk capital, venture capital that we invest into unique projects.
So at Airbus, you didn't only work on the space plane, yet other projects as well. One of them might be politically very much talked about right now, FCAS.
Yeah.
So I don't know, for sure you can't tell us much about it because it's a classified project. But how does it feel being involved in a classified project in general?
To be honest, it hasn't been really different from other projects. So we had to sign a lot of paperwork for confidential stuff. But from engineering point of view, it didn't make any difference, to be honest.
Okay.
So when you start working on the topic itself, it feels same, especially when you work on what we call the air vehicle or the airframe. So the airframe is nothing that is related to armament, that is related to the defense stuff, which is part of the project. So it feels like any other project, to be honest.
Yeah, that's what I was wondering about. If you even feel connected when you work on military defense systems or something, but you're not really involved in the weaponry, but mainly on the air structure.
Yeah, that's true. Absolutely. Yeah. So there are some interaction points, just because, of course, a military vehicle is a different one. But it's a more exciting one, to be honest. So each military vehicle is unique. That means you have to think about so many things where there's no solutions so far. And this makes the collaboration with the colleagues really unique. And the European environment is really complicated one. That means you have so many requirements addressed by the member nations, and putting them into one military vehicle is, from technical point of view, a big challenge. So for me, it never felt really different from working on a civil project from engineering point of view, but the technical detail is really different, and working on a military project is, to a certain extent, more exciting.
More exciting, yeah. I can imagine. But are you allowed to tell us what was the main purpose of your or the part you were doing on FCAS? Yeah,
that's easy to say. So we are in charge of the air vehicle, and the air vehicle, in the engineering term, is the airframe. It's the outer aerodynamic shape and the internal structure. So though I've been part of the structure development, we were in close collaboration with all the other disciplines, so aerodynamics, loads. And since I've been leading the multidisciplinary optimization at Airbus Defence and Space, multi means really multi. So you have to incorporate all the other disciplines simultaneously, and you have to fight technically about what requirement is the most design driving here and there. And so mainly I've been involved in coupling all of those disciplines in order to find the best, I wouldn't say best compromise, just because optimization is all the time finding a compromise. But at the end of the day, is finding a trade-off of all the disciplines in order to provide the best performance for the vehicle. So this has been my work.
Okay, and on FCAS, maybe not all of the listeners right now know what FCAS initially is, and that it has part of the, let's say, of the aircraft who's working by itself, by an unmanned vehicles, and there's a system, like communicating with each other to increase the performance of and the knowing of the jet. So and right now in America there was the B-21 launched or publicated, as you would say, and it has some similarities to FCAS in a way, doesn't it?
It does, yes.
Yeah.
On the other hand, as you mentioned, so FCAS is less an aircraft. It's by no means an aircraft. So there is an aircraft or many aircraft types involved, but it's, as you mentioned, it's a system of systems. So it's a future combat air system, coupling satellites, cloud computing, aircraft, but also ground stations and many others. So the aircraft which I've been involved in is only a small piece in a bigger system.
I was wondering about the B-21 because it's a blended wing air design, which you also worked on at Airbus.
Yes, so a blended wing is for me, to be honest, technically a different aircraft. Why? So military aircraft tend to have what we call delta wings, and delta wings are a huge wing like the Greek letter delta, so that triangle, and it looks like a blended wing body.
But it's not?
It's working differently. So a BWB has a higher volume in the fuselage, and the distinction between wings and fuselages disappears totally.
Yeah, in a blended wing design.
Exactly, in a BWB. And for the military aircraft, like the FCAS designs that are flowing around, or the American ones, they are still delta, double delta, triple delta wings. But you are right. So the difference is a kind of transient one. So there's no clear distinction between both. Yes.
To stay at the blended wing, what are the biggest advantages of the blended wing design? What you say?
Let me put it to say it in to be a bit provoking in this direction.
Sure.
There will be no new civil aircraft which looks like the current civil aircraft that are flying. Just because the aircraft currently, or the designs we have today, which are based on kerosene or on burning, on breathing devices or breathing engines fueled by kerosene, reach the maximum we can reach today. And you could improve here and there a little bit. And from environmental point of view, I don't think that we should afford having the same design and the same fuel system as we have today. So we need different solutions. And the BWB has been in the past one of the biggest changes that improve the aerodynamics, improve the structure performance, and has a very big disadvantage that it changes the infrastructure of all our airports.
Yeah, that's what I was going to talk about, because there are a lot of challenges coming with the new aircraft design.
Absolutely. And this is the reason why the BWB is, if you stick to the current infrastructure in terms of fuel system, maintenance system, airport infrastructure, is a death birth. However, since we have to change, and now it comes, probably the most interesting part about the BWB is the volume. Yeah. You have a lot of volume inside the aircraft, and if you take a look on the current challenges on switching from fossil fuels to hydrogen, it is volume. So hydrogen is great. It has an issue that it requires, for the same power density you need to fuel a complete mission, you need much more volume.
Yeah.
And the BWV comes here into play. I'm sure that it might be too provoking or too much in the future a prediction, but the next civil aircraft that will be successful, it will be a hydrogen based one with a BWP design.
The hydrogen 0E series of Airbus has one BWD design as part of the lineup, but also some old aircraft look with a normal fuselage and wing. What do you say about this? Do we even need the old old designs of an aircraft?
You will all the time have a transition. So industry is mainly, if we come to the European DNA, we are quite careful. I wouldn't say the others are not careful, but we are more careful in that regard. That means there will be a kind of transition. We will be testing the new engines, the new fuel systems, all the challenges coming with them on traditional aircraft, like the A380, like it happens now, in order to learn how things work and evolve. And afterwards, there will have to be a change in the design. Just because changing the fuel system, the engines, changes the design. And aircraft and all the students upcoming will not yet know that aircraft are incredibly sensitive creatures, if to say. So they are very touchy. If you move the engine a little bit, if you move this and that, you totally change the design.
Creating
and this is the reason why we will have to change to something different than we have today.
I think we got a lot of information from you about the blended wing design. But right now, due to our setup, we have to do a short break and have some university politics.
University politics, what even is that? University politics is the general term for all aspects in which student interests need to be represented towards the university. Representations occur on all levels of university. Those levels being the individual cohort of a study program, meaning the group of all students that started a certain study program in a given year, the study program as a whole, for example, aerospace or geodesy, the student council, for us, our student council of aerospace and geodesy, the school, our School of Engineering and Design, the entire university. On these levels, there are always two branches of student representation: the committees and meetings where we actually talk to people from the university, and those meetings where just us students get together and discuss what the opinions that we represent even are. Those meetings of students are also the places where we decide who gets to go to official committees.
Now we are back from our small break. Our next topic is aeroelastic tailoring. Could you explain this in a very short sentence, maybe?
It is a very old and ever young technology. So in a sense, it is the interaction between a structure in the air. If the air is flowing around a structure, it deflects, so there's a deformation of the structure, and it affects again the aerodynamics, the air flow. And this interaction can be used as a design parameter. And this is exactly aeroelastic tailoring. So to control the interaction between a structure and the air flowing around the structure, like a wing, for the purpose of improving the overall design.
Yeah. Would you say we have right now the optimal performance?
Oh, no, by far not. There are rarely wings that are really aeroelastically designed, partially, but not to a full extent. And we shouldn't forget that aeroelastic tailoring has two dimensions, what we call the passive aeroelastic tailoring and the active one. The passive one means that the structure and the air flow interact as they are built without any kind of interference by human being like the pilot or a computer. And the active one is there is a computer in the loop. There are sensors that measure the parameters like speed, pressure in the wing, and when it is required, they will move some hydraulics or some actuation systems, and you change the shape of the wing during flight. So this is the active aeroelastic tailoring. And with the passive one, we are not yet where we could be, and by no means with the active one. So it is still a lot of room for research, education, and there are still room for you when you come to aerospace engineering to work on that.
Yeah, so we would say there's a lot of room for improvement.
Absolutely, absolutely. So if you go further, incorporating new materials that are morphing capable, having morphing materials in the airfoils that interact with the sense of aeroelastic tailoring, you would have aero, structure, materials, and computers, so the control systems. And this is MDO, this is multidisciplinary optimization, which we will need for the next generation of aircraft to come.
So as you already mentioned, MDOs are a big part of aeroelastic tailoring, and to improve the aeroelastic tailoring, so we achieve better results in that. But before we move to that part, because you went back from industry into research, and on the topic you wrote your PhD about, like multidisciplinary optimization, design optimization, or as we will call it, because it's such a long term, MDO. But before we talk about this part, maybe you can tell us what are the biggest differences between working in the industry and at academia.
So I had 2 phases now in academia. So during my research and my PhD, and now coming back. So from this second stage, it's rather short term to make a conclusion. Nevertheless, generally speaking, the work in industries is driven by profit. You have less freedom for what we call the fundamental questions. And sometimes when you have to develop a product where you are aiming at big leaps in the design, you have to go to the fundamentals. And this is where I think our industrial, so the collaboration between industries and academia could be improved. Just because I don't think that the industrial or the companies will be so much willing to invest into fundamental research. And to have an industrial-driven fundamental research, we need that link between academia and industries. And this is where I think, so working in academic design, in academic research or in academia has a lot of more freedom. And I think we could improve also in this regard if we at least partially align this degree of freedom with the demand coming from industrial application.
So if you would say what of the differences you just mentioned would be the one who made you join academia again?
It is definitely the freedom to realize ideas you are convinced in, where the industrial framework and setup is not willing to invest money in. Yeah, so where we have to go to some fundamental research and some more courageous approach towards uncertain outcome. And this is research. It's all the time uncertain outcome. This is pushing me back towards academia.
So, and since you joined academia right now and went back to your research about the multidisciplinary design optimization, or MDO as we will call it furthermore, maybe you can talk us through what MDOs are, or why is it so important for you?
Yeah. So I could talk for hours about that. So let's keep the long story short. but by having a kind of background of what is expecting us, what is in front of us. So in the 70s and 80s, the aerospace companies were populated with hundreds, if not thousands, of engineers doing hand calculations. With the appearance of personal computers, so we had computers that time, but they were not accessible by everybody. With the availability of hardware, the software evolved, and we do have today numerical simulation methods that are the standard. Nobody will work with hand calculations, at least not in the industrial scope. And this revolution, I would say, is the smaller one compared to the evolution, probably the revolution, when we go towards a multidisciplinary design. Why? Multidisciplinary designing a product means you don't design the product from one or monodisciplinary point of view. You don't take a look on, let's take an aircraft and design the aircraft from aerodynamic point of view, freeze the design, go designing the structures, freeze the design, and equip it with systems. But this is exactly what we are doing today. It's a bit of black and white. There are loops, there are interactions. Nevertheless, in a sense, this is the way in industry how we design our products in general, a sequential design. And now let's take a rather simple to understand example where it becomes really apparent to everybody that this doesn't make sense. Let's take a wing. If you make the wing thinner, you improve the aerodynamic performance, but increase the weight of the wing and decrease the structural performance. And the question is, what is the best one? The structural guys want to increase, the aerodynamists want to decrease. And what do we have? A kind of which engineering means do we have in order to increase the capability of the whole product? The only way is to consider the disciplines simultaneously. Yeah. Most of the disciplines counter-react, or they are working against each other in a design.
Yes.
Especially in a quite a sensitive design like an aircraft or an air vehicle.
That's why you have some like different designs when you're making an aircraft, and like if one thing doesn't work out, you switch to another one. So you design multiple ones at a time. But this is where multiple MDOs come in and maybe improve this process.
It will change the process of development totally, just because you will be capable of doing or considering all the requirements to the product, and the product finally will not distinguish between the requirements. It will have to fulfill all of them simultaneously, to consider them simultaneously. And MDO is not a technology that you use in order to, let's say, to decrease the weight of the final design of an aircraft. This is a big misunderstanding. It is a design methodology you use from scratch. You have a blank sheet of paper, and you start by having a piece of dough, which you shape towards your product. And you let all of the ingredients, which I call the requirements, customer requirements, certification requirements, environmental requirements, operating requirement, to shape that design. And the mean of shaping that design is MDO. So you have powerful software, powerful engineers with enough education and understanding of how these things work, and you start shaping that design simultaneously, considering all the requirements.
So you're saying it will happen, it will be, but do you think you can imagine when it's actually gonna happen? Do you have like a year in mind? You would say, okay, at this year we'll definitely have some MDOs, maybe not the best MDO it's possible, but
yeah, That's really hard to answer question. MDO is not a new technology. So, let's step back to the argument or to the topic of having numerical simulations. We had the methodology of numerical simulation in the 50s, but you couldn't realize them until we had computers. And it took, to be honest, also a kind of cultural change to convince the people that you can believe that bloody computer. That really happened in industrial application. The honest hand calculations are the best. So you would have heard that until they were outdated. And the same will happen with MDO. So coming back to your question, MDO is a rather mature technology today, though we have still a lot of things to improve, just because we don't use it in application as a standard way of working. When it comes, we will have to spend a lot of research into. Nevertheless, I think that the complexity of our new products, like a BWB, will force also the industrial application to employ MDO. And this is one of the reasons why I'm coming back to academia. I think one of the bottlenecks is a cultural one. It's a mindset. And if the people don't enjoy an MDO education at university, they will not have the mindset in industrial application, and they will resist changing the way we do that since hundreds of years or 100 years. And this is the reason why I'm really keen on setting up a fundamental MDO education in order to change that mindset. So it's, I wouldn't say less, but it's equally important from mindset point of view and from educational technological point of view.
So there was like one goal for the future. Do you have like any other goals for the next past years?
For sure. So on the one hand, education is something which is linked to passion. So I feel that I achieved all what I could achieve in industrial application, and I'm here at TUM in order to educate people. So I'm really keen on educating the people, and I think that we have there are many ideas to improve our education, to have a much more high interaction between the students and the teachers. I think that the way the teachers standing up front and teaching something will remain. Nevertheless, it is not the efficient method. So I think I would like to improve the tuition in terms of a project-oriented tuition, that we have much more projects that we work jointly, the students and the teachers, on. What I think is also very tempting for me is to add that flavor of practical application to a very practical oriented education like aerospace engineering. So it's for you, I think, and I will ask you for your feedback in the course of the next months and years to come. It's more interesting to learn theory and really complicated stuff if you know why you're going to use that, and if you have the application in front of you. That means the project and the next collaboration with the industry, the next, I don't know, master thesis, bachelor thesis, project, scholarship, whatever, which you do directly on site with the practical guys. And this is where I think that my network in the industrial application might help to set up such a kind of slight change, hopefully with a good impact on the students, where you have more hands-on practical application.
Yeah. Do you have anything else that you want to tell the audience?
Also, for the moment, to be honest, I'm really happy if I get my lectures done. It's really, and I wouldn't say I underestimated that. I haven't never gave it the thought how it will be. I've been just keen on working with you, but it's really exhausting to prepare lectures, to spend nights in thinking how you could explain that better. But I will. So the next step in my own evolution, in my advancement is clear. So I will, in the next semester, for example, start practical projects with the students. I will start the PhD education of my PhD students, and where I think will be a milestone in the collaboration between TUM and aerospace engineering. I would like to sign a collaboration, an open-ended collaboration with the industrial partners, where we don't share only the fundamental research, but we share also the software. That means we will be hosting, hopefully at TUM, real-life software from industrial partners, where the students get hands-on the one hand, and PhD students included, and on the other hand, the industrial application will get directly the feedback and the latest development we have at TUM, getting them back into our European industry.
Would Airbus be your dream partner because you work there?
Absolutely. So my colleagues, so it would be for sure my first partner to speak with, but not the only one. But for sure, it will be the initial partner, just because, a few months ago, I've been sitting with my colleagues, drinking coffee and tea and talking about how to improve things. And when it became clear that I will be moving to TUM, we talked also about the next step. How to improve the collaboration between Airbus and the education and the research. And exactly these thoughts were part of this, I wouldn't say strategies, it might get a bigger strategy, but at least this endeavor to get a closer collaboration between industrial application and TUM.
That sounds like a promising future.
Sounds great.
Thanks again for joining us today, and have nice holidays.
Yeah. And we have to make a small shout out to the Student Council for Sports and Health for renting us their equipment. And as always, Professor van der Hout was here as a scientist, like all the professors will be. So thanks again.
Many thanks for hosting me, and good luck with I like this format of having a very close interaction between the students and the teachers. I think all my colleagues, the professors, will be more than happy to support that. Thank you for having me here.